Swayam Prabha. Digital India. Educated India.
So you can practice different questions on having a different kind of sources. So let us consider one of the example where we can solve this or use the another method. So what we can do, we can consider the same question and we'll write the nodal equations. Suppose this is the question. Okay, so we have taken the same example. Now we'll write the nodal analysis. So first identify the total number of nodes. So we'll not use any kind of okay, so how many nodes are there in this circuit? So this is the reference node. So let us assume that this is a node 1 and this is the node 2. Okay, so total number of nodes we have identified 3, out of which this node 3 is reference node. So we'll be applying our nodal equations at 2 nodes. Okay, now what we can do in this particular case, we can write the nodal admittance matrix. Okay, when we write the nodal admittance matrix, the total admittance connected to this node 1 is nothing but 1 by J4 plus 1 by 2. So this is J4. Okay, and the common is minus 1 by J4, minus 1 by J4 between the node 1 and 2, and the total node 1 is nothing but 1 by J4 plus 1 by minus J2. So this is the admittance matrix. Okay, so this is basically the Y matrix, which is nothing but nodal admittance matrix, and this is multiplied the node volt current. These are the unknown voltage, and the current source which is connected to the node 1 is 4 angle minus 30, which is approaching the node, and node 2 is 0. Okay, now let us solve. So we can now solve this equation, right? So this is the way how we are going to solve it. So we'll be solving it directly for V1 and V2, where V1 is nothing but the V0 and V2, so we can write it here. So V0 is nothing but the V1 and I0 is nothing but P by minus J2. Okay, V2 by minus J2, and V2 also is 3V0, so basically 3V1. So this you can solve. So this is how we are going to do the nodal analysis. So we can use this matrix and solve the circuit. Let us now look into the some of the questions which we will be using based upon some theorems. Okay, so the theorem which we have studied is Thevenin's and Norton theorem. So let us consider an example where you will be using the Thevenin's theorem. So consider one example. We have a resistance so this is the circuit. So the voltage source, suppose 10 volt, resistance is 2 ohm, this also is 2 ohm, the current is going upward as 10 ampere, and this value suppose 1 ohm and 3 ohm. So question statement is determine the current through the resistance, determine the current through the resistance of 3 ohm. So suppose this is the current I. So we have to find the current I. So let us separate this out. Okay. The first step is remove 3 ohm resistance from the circuit. Okay. So we have to remove the 3 ohm circuit without the resistance between the terminal A and B. So redraw the circuit. So we have a resistance here, a current source, and 1 ohm resistance is here, 2 ohm is here, 2 ohm is here, we have 10 ampere here and 10 volt here. So this is the remaining circuit between terminal A and B. Now Thevenin's theorem says that we can replace this complete circuit by one circuit of this kind. Okay, so this is nothing but RTH and this is VTH. So this is the Thevenin's theorem. So we have to convert this to find out the RTH and VTH. Now let us see by how many methods we can solve this circuit. So in first method, what we can do, we can convert this current source to a voltage source. Okay, so this current source of 10 ampere between this node, suppose M and N, is replaced by a voltage source in series with the current. So let us consider first method by which we are going to solve it. So the circuit will be getting modified. So let us redraw it. We have a resistance, then we get one more series resistance and the voltage source. Here we have a voltage source already, and then this goes as 1 ohm. So this is how the circuit will look like. This is 2 ohm, 1 ohm, 2 ohm, and the voltage source will be here at 20 volts, correct, and then plus minus 10 volt here, and this is a B terminal and this is A. Now the idea is to find out the open circuit voltage between the terminal A and B. When the terminal A and B is open, no current will flow through this 1 ohm. So whatever voltage will appear here is the voltage, open circuit voltage between terminal A and B. So we can write it VAB is nothing but a 20 volt, and suppose there is a current I flowing in this circuit. So 20 volt minus 2I, this is the VAB. Okay. Now let us apply KVL in the loop. Okay, so in this loop if you apply the KVL, we'll get 10 minus 2I minus 2I minus 20, nothing but 0. So if you solve this, we'll get I as minus 2.5 ampere. Okay, so we'll get minus 10 by 4, so it is minus 2.5 ampere. That is a current which is flowing I. It means that okay, so now what is the voltage? So we have written already 20 minus 2I. So voltage is, that is open circuit voltage VAB between the terminal A and B is nothing but 20, and this drop will be here in this volt, so here it will be plus, okay, because this is going to be the drop which has to be added between the two terminals. So there is a 20 volt, then this drop will be added to make this voltage, so it will be 20 minus 2.5 into 2, which is nothing but 15 volt. Okay, so open circuit voltage is nothing but the 15 volt, and RTH, what is the Thevenin's equivalent resistance? Okay, so for calculating the RTH, which is nothing but replacing all, turning off all the sources. So suppose we want to redraw the circuit by turning off all the resistance, so we have one here, and this voltage source will go in the short circuit mode, and this current source will go to the open circuit, and we have one, this RTH is the Thevenin's equivalent between the terminal A and B. This is 1 ohm, 2 ohm, 2 ohm. In this circuit clearly you can see these two 2 ohm resistance are in parallel, which is in series with 1. So RTH is nothing but, will be coming out as 1 plus 1 2 cross 2 by 2 plus 2, which is nothing but 2 ohm. Okay, so RTH is 2 ohm in this case. Now is there any way by which we can solve this circuit? Okay, so let us consider another method. which is the source transformation. So we have solved this by using mesh analysis. Now let us find out using source transformation. Okay, so let us draw the circuit again. This is a battery or a DC source. Here we have a current source. Is connected with the terminal A and B. So this is the circuit. Okay, so this is 1 ohm, this is 2 ohm, this is 10 ampere, 2 ohm, 10 volt. So in this circuit, if we apply the source transformation and convert this part of the circuit as a current source, it can be done because the voltage source is in series with the resistance. So the circuit can be redrawn as this way. So this is using source transformation, correct? So in this circuit, if you are applying source transformation, the resistance will be same as 2 ohm. This is anyway 2 ohm which is not disturbed. This is 10 ampere. What is the value of this current? This is Vs by Rs, which is 10 by 2. So this will be nothing but 5 ampere with this direction. Okay. Now the two current sources are in parallel, so the current rating will get added up. Okay, so this current source will become as 15 ampere, and these two resistors are in parallel, so equivalent resistance will be 1 ohm. Okay, so this is between these terminals, and then we have 1 and 2. So this is terminal A, this is terminal B, 1 ohm, 1 ohm, 15 ampere. Now once again, what is happening here, we have replaced this current source as 10 plus 5. Okay, so now we'll be again using the source transformation, so we can convert this as a back to a voltage source. Okay, this is A, this is B. Between terminal A and B, 1 ohm resistance is there. So 1 ohm, this means after source transformation, this will be 1 ohm, and this is current into resistance. So 15 ampere into 1 is nothing but 15 volt, and the polarity is this. So you can see that open circuit voltage, there will be no current. So the total voltage appearing between terminal A, open circuit voltage between the terminal A and B is nothing but 15 volts. Okay, so this is the VTH. So VTH is nothing but VAB, which is nothing but 15 volt. Okay, here in this case you can find out only using the source transformation. So I have not written the equations, so if you practice you can get it and apply this. So there are multiple ways by which you can find out the open circuit voltages, and RTH will anyway will be same, which is the equivalent impedance between the terminal A and B, or the resistance between the terminal A and B. Now let us use or solve this circuit by using superposition theorem. So for example, the same circuit, we are using by superposition theorem. Okay, so this is the terminal A, this is B, and suppose this is your 1 ohm resistance as usual, this is 2 ohm resistance, this is 2 ohm, and this is 10 ampere, 10 volt. So this is the circuit. Now in this circuit, apply superposition theorem. If we apply the superposition theorem, so we'll be considering the source one by one. So consider only the voltage source. Okay, so while considering the voltage source, we can consider only 10 volt. So the circuit, if we redraw, it is nothing but this will be open circuit, so no current will flow, and this is nothing but this way. So this is 10 volt, this is 2 ohm, this is 2 ohm. So A and B. So if we apply the KVL in this loop, so 10 minus 2I, suppose this is the current I1, so 2I1 minus 2I1 is equal to 0. So I1 is nothing but 2.5 ampere. So the total current, if we just mark the direction of the current, so what is the voltage here? Whatever the drop here, that voltage will appear. So VAB is nothing but 2.5 into 2, which is 5 volt. This we can even use the voltage divider rule. So similarly, VAB is nothing but 10 times of 2 divided by 2 plus 2. It is 5 volts. It is using voltage divider rule. This is KVL in loop 1. Anyway, there is only one loop, so this loop, this is the voltage. Now consider only current source. Okay, so when we consider only the current source, then let us draw the equivalent circuit by turning the voltage source off and current source will be turning it on. So this voltage source will be off, which is short circuit, and here is the resistance. This is your current source. This is the terminal A and B. Now we are using only the current source for the energizing the circuit. Okay, so this is 10 ampere, this is your 1 ohm, 2 ohm, 2 ohm. Now pay attention clearly. If you want to see where this 10 ohm current is going, so 10 ohm current will go here and get divided into two currents, I1 and I2. So in this case, if we apply the current division rule, if you apply the current division rule, what we can find out? The I2 is nothing but 2 times of I by 2 into 2, and this I is nothing but total source current, which is 10 here. So it is 20 by 4, that is 5 ampere. So what is the voltage across this 2 ohm resistance? So voltage across AB in this case, VAB due to voltage source, now VAB due to current source is nothing but 2 into 5 is 10 volts. Now superimposing the response. Okay, so now superimposing the response, we get VAB due to the voltage source plus VAB due to the current source. 5 plus 10 is nothing but 15 volt. So there is a multiple ways. I have demonstrated here 3 methods of finding the VTH. So you can find the VTH very easily by using any of the method and then equivalent resistance as RTH. Okay, so this is how we can solve it. Now we have converted the complete circuit as an equivalent VTH and RTH. So this is basically the equivalent circuit. Now connect the 3 ohm resistor. This is 1 ohm and this is 15 volt. Now the current I is nothing but 15 by 3 plus 1. Okay, so the current which we are finding sorry, RTH is 2 ohm. RTH is 2 ohm. So the current is nothing but 3 plus 2, which is 15 by 5, 3 ampere. So this is the answer. I is nothing but 3 ampere using this method. Now in the continuation of this, if we find out the Norton's equivalent circuit, okay, so in Norton's equivalent circuit we'll be able to solve this by converting this into a current source in parallel with the resistance. Okay, so the Norton resistance and Thevenin resistance will be the same. We can find out. So let us consider a small example, maybe a different example. So let us consider a circuit which is of this nature. So now you have a 10 ampere current source which is going to a resistance here as a 1 ohm. There is a battery, DC source, resistance, this is the circuit. Now assume this is the 2 volt, 1 ohm and 2 ohm. So this is the question. Okay, so what is the question? Determine the voltage across the 2 ohm resistor. Determine the voltage across the 2 ohm resistance. The 2 ohm resistance is here. We have to find this V naught. So let us consider this. So step 1 is to remove that element. So when you remove this element, the circuit will become very simple. You have a current source, a parallel resistance, and the remaining battery. This is your remaining circuit. after removing between the terminal A and B the 2 ohm resistor. So this is this way, and the drop voltage of 2-volt battery. Okay. Now in the circuit, if we first find out the Norton's current, right? The current through the short circuit may be determined by the superposition. So for finding out the Norton current, right? So we have to short this. So when we short the terminal A and B, this is known as the IN. So finding the IN, what we can do, we can either use the superposition theorem, okay, or we can use it by any of the methods. So let us consider the superposition theorem. So now finding IN using superposition. So let us consider the superposition theorem. So we'll have one source active at a time. So let us assume only 10 ampere current source is active. So when we assume a 10 ampere current source active, we can redraw the circuit. The voltage source will be short circuited. So 10 ampere source is active. Then we have a resistance. This will be replaced by the short circuit. And this is the equivalent circuit. So here it was the voltage source. So this is the IN. This is 1 ohm and this is your 10 ampere. So here if we apply the current division rule, the current which is entering here at this point gets divided here. So let us suppose I1 and I2. So IN is nothing but I2, which is 10 into 1 by 1 plus 1, which is nothing but 5 ampere. So IN is nothing but 5 ampere due to only voltage source, current source. So I and I. So where I and I is due to current source. Okay, so I and I is I2, which is this. Now consider the voltage source. And turn off current source. In this case, the equivalent circuit will look like this branch will be open circuited, which carries the current source. You have a 1 ohm resistance here, then a battery of 2 volts, correct, and then we have a this circuit. So in this condition, whatever the current will be flowing is nothing but INV, and INV is the current IN due to only voltage source. Okay, so now if we apply, current will flow like this. So we apply KVL. INI is nothing but P by total R 1 plus 1, and V is nothing but 2. So this is 1 ampere. The current IN is 1 ampere in the same direction. Okay, so when we superimpose this, now applying superposition, In is nothing but I and I plus I and V. So due to the current source and due to the voltage source, this is 5 and 1, total 6 ampere. In is 6 ampere. Now we have to find the Rn. Now find the value of Rn. So Rn is the equivalent resistance between terminal A and B, keeping all independent sources off. If there is a presence of dependent source, we cannot remove it. Okay, so now let us draw the circuit by turning off all the sources. So the current source turned off means this will be open. There is a one resistance, then the voltage source will be short circuited, and this is another resistance. So this is the equivalent terminal A and B. So this is nothing but Rn. So Rn nothing but 1 plus 1 is 2 ohm. Okay. So the Norton's equivalent circuit means we have converted this complete circuit for 10 ampere, 1 ohm, 2 ohm. Let us, this is 2 ohm, this is 1 ohm. Now this circuit is converted between the terminal A and B as 2 ampere, 2 ohm, this is also 2 ohm, and this is IN, which is 6 ampere. Okay, what is the voltage between terminal A and B? The voltage between the terminal A and B is nothing but 6 volt. Okay, so voltage across 2 ohm is nothing but I, which is IN into 2 by 2 plus 2. How much it is? 3 ampere. Now the voltage V0 is nothing but I into R, or this is basically 2 ohm. So 3 into 2, which is 6 volt. So V0 is nothing but 6 volt. So this we have done using Norton's equivalent. Similar method we have to apply for a DC, where the quantities will turn up in the terms of phasor and complex. That's all. Just the process is quite similar. But when the circuit is having a dependent source, in that case we have to apply some theorems in which we cannot replace it. What it means is, the quantities on which the dependent source is dependent, that should be unaltered, and using any of the superposition or suppose mesh analysis or nodal analysis, you have to keep that source into the consideration. Okay, and the superposition is only valid for independent sources, and the dependent sources will be kept in the circuit as it is during the application.